about quenching timescales. And the reason I think this is an interesting topic or an interesting approach is that quenching timescales, I think, tie to quenching mechanisms in a fundamental way. So it helps us explore what mechanisms are responsible for quenching when we try and constrain the timescales in which galaxies quench. So, at risk of repeating some of the things that Frank said this morning, one of the nice things about star-forming galaxies that we now understand is that they live on a star formation main sequence. Sorry, Julianne. Where
you modified it, so it's
I modified it. Where galaxies of a given mass have a narrow range of star formation rates, and basically pretty much all star-forming galaxies live on this main sequence. And so all that happens with redshift, as you go up in redshift, the star-forming main sequence just shifts up, in fact, so that endpoint, as far as we can tell, doesn't really move. And so the fact that star-forming galaxies live on this main sequence is a nice constraint when we try and want to understand quenching. So there's one nice fact about the main sequence and the actual parameters of the main sequence is if you put a galaxy, a star-forming galaxy, down here, say, at high redshift, and you follow as the universe sort of decreases the amount of star formation, the absolute star formation rate of the galaxy stays roughly within a factor of few constant. So a constant star formation rate is actually not such a bad model for the evolution of a single galaxy. So quenching in this case is basically, in the way I use it, is moving off the main sequence and ending on this pile of corpses of dead galaxies. And so understanding how, why, and how fast that arrow moves, that is what I think is the interesting question. So before I move into data, I want to go into even more bit of a background. So I think quenching timescales are deeply related to what happens to the gas in galaxies. And so one of the sort of theoretical insights that the existence of the main sequence has brought us, there's two key papers, one by Boucher a couple of years back, and then another one by Lilly, where they use sort of modified bathtub models describing galaxies in a very simple way, where galaxies have a gas reservoir, out of which they form stars. They have an inflow, a cosmological inflow of gas, and then they have an outflow driven by feedback. And there's fundamentally two ways in this totally simplistic model in which you could shut down star formation. You could just shut off the inflow, in which case the galaxy is still left with a gas reservoir, and then it will slowly eat up that gas reservoir. You have gas in a disk, maybe even a halo, which can still cool down. And what happens is that galaxy will continue forming stars for quite a long time. So basic parameters, you can work it out. You go in an exponential tailspin with a tau of order a gigayear, where that order is really hand-wavy. The point is it's slow. So you can, quote-unquote, quench a galaxy or set it on a path towards quenching without much changing, and I'll get back to that in a minute. The other way, of course, in which to quench a galaxy is you nuke its gas reservoir, and then the star formation rate goes from whatever it is to zero, or effectively zero. Sufficiently many orders of magnitude down that it is clearly no longer a star former. So, how does this manifest? So this is the general galaxy color mass diagram. This is the blue cloud, red sequence, green valley. Don't ever look at this diagram again, it's a red herring. Instead, look at these diagrams where split by morphology. I'm going to do one more step. I'm going to remove dust because this is Sloan data, so it's easy to do. And what you notice is that this sort of green valley or color bimodality pretty much disappears. Look at just the late types. You see down there, where's the pointy stick? So this is basically the equivalent of the main sequence. And you see this tail of late type galaxies all the way to red colors. And so these guys, this diagram, if it just shown you this, you would not draw these green valley lines. There's no bimodality here. There's simply the star-forming population in a slow tail quenching at high masses. If equivalently you look at just the early types, you again see the red sequence uses long tail to the blue. Again, not really a bimodality, and where exactly you draw those lines isn't really obvious. So if galaxies quench, both early and late types, as they clearly do, some of them get red, there has to be a source population down here that moves up rapidly, and the source population down here is the disks on the main sequence, and they must move up very, very slowly.
I feel like I have to ask about your confidence about the dust correction, because that
Yeah.
would be quite important.
We're basically doing an SUV fit, and so in the Sloan universe, the corrections aren't large, and you can verify this with a sort of a UVJ diagram. I wouldn't really trust this at high redshift, at low redshift we can do this fairly well, and the typical corrections are small.
I've not found that personally when I've done this.
So all that happens is basically, if you see the slope of the main sequence is, as the absolute star formation rate increases, you get more dust, and so once you correct for dust, the slope of that moves down. The point here is really, actually, that the green valley doesn't empty. The green valley isn't built of dusty galaxies. There are some, sure, they move out, but that's not the galaxies that live there. So another way of showing that is by coloring sort of each little cell by the median SSFR. And so what you learn is both really interesting and actually, again, really misleading. So in both the case of the early type galaxies and the late type galaxies, the quote-unquote green valley population have depressed specific star formation rates. So they're in the process of quenching. They've already moved off the main sequence. But that doesn't, again, tell you anything about quenching timescales, except maybe from the context that there's very few of the early types and there's an awful lot of the late types in that space. So what I really want to do is measure the rate of change of the star formation rate in green valley galaxies. And that's hard, so for now I'm going to, in a very hand-wavy way, in a broad way, try and constrain it. And what I'm going to use is this diagram. It's now a color-color diagram, no longer a color mass diagram. On the x-axis is U minus R optical color, and on the y-axis is NUV minus U UV color. And so those two colors probe different timescales. And so down here, this is the blue cloud, this is the red sequence. And I've colored in these two different contours here, the green valley early and late types. And so what you see is green valley late types are still blue in the UV. They're still somewhat star forming. There's still some blue young stars there. At the same optical color, the early types are much redder in the UV, indicating they have no ongoing star formation, giving you the first clue that this kind of color-color diagram gives you that age spread, or that tau spread in how galaxies quench. So I'm just going to show you briefly how the population just of late types and just of early types look, and I'm going to explain these lines that I've overplotted here now. So what I've done is, I've done the simplest thing I could do. I've taken this idea that galaxies have a constant star formation rate, and then at some time t, a quenching event happens. And then the galaxy has a choice of paths. It could drop its star formation rate to 0 and continue as a totally dead galaxy. Or at the other extreme end, it could go into a very long exponential tailspin with a tau of 2.5 gigayears. The large points here are 1 gigayear time intervals. The small points are 100 million year time intervals. So we can now go back to these diagrams and show how galaxies move on it. So the first track I'm showing you, follow the red dot, here, here, and here. Follow the red dot. I'm going to quench a galaxy really, really rapidly. What happens? Because the star formation rate drops so fast, the UV goes red very quickly, whereas the optical lags behind. Show that one more time. So these tracks, these rapid quenching tracks, go through the population of these green valley early type galaxies. I can do the same thing now for a very, very slow quenching track. And there's a fundamental point here. So I'm going to quench a galaxy very, very slowly. Look particularly at this point, starting in the blue cloud on the main sequence. What happens when I quench it slowly? 4 gigayears after I transition the galaxy to an exponential decay, you have barely entered the green valley. So this is another way in which the green valley is a red herring. If you want to understand what quenches these galaxies, don't bother studying them. Something happened to their ancestors, billions of years ago, and we're only now seeing the after effects. I've compared this to zombie galaxies. So they're already dead, but they're still moving. So in contrast, something has to happen that's pretty dramatic to these early type galaxies, because just a few 100 million years later, we see them essentially quenched in the green valley and then the red sequence. And I think this dramatic event is related to merging activity. So here is one blue early type galaxy that is optically blue, still star forming, in stripe 82. So if you look at the deeper image, this is what you see. And in fact, if you take those blue early type galaxies that are in deeper imaging, you find a very high incidence of merger features. So these blue spheroids, I think, are newly created, or even if one of the progenitors had a spheroid already, there was a smash, boom, you get the picture.
But, I mean, often those kinds of shells tend to be very long-lived, right?
Sure. So Yes, so if you plot the fraction of these things that have merger features as a function of color or time or something, it decays very rapidly as you would expect. Okay, so what can we learn from quenching timescales about the process that's involved? So I sort of intimated that late-type galaxies quench slowly, early-type galaxies quench rapidly. So I did the simplest thing, I checked the environment, and again I did the very simplest thing I could think of. I took the Young halo catalog and I split by halo mass at 10 to the 12, because that's the magic mass. So if you look at the early-type galaxies, they kind of exist, so the quenching early-type galaxies, they kind of exist in both environments. You know, there's certainly first and second order effects, but to zeroth order, it happens in both kinds of environments. If you look at the late-type galaxies instead, you find that the blue sequence star formers basically all live in low-mass halos, and the quenched or quenching late-type galaxies, they almost all live in high-mass halos. So there's two particular late-type galaxies that are in this process, and they're the Milky Way and M31. This is from a really neat paper by Darren Croton's group, where they worked out the color and star formation rate of the Milky Way, and as best as they could do based on archival data, they think the Milky Way and M31 are way below the main sequence. And this kind of makes sense. If you think about it, if the Milky Way and M31 were on the main sequence, the star formation rates would be hugely higher. It also means that in this broader picture that I'm trying to present here, the Milky Way and M31 were quote-unquote quenched and left the main sequence many, many gigayears ago. And this makes sense with the sort of smoothly, slowly declining star formation history. Okay, so the $1 million question is, of course, what about AGN? Is there any evidence for feedback?
Sorry, was that a model plot?
This?
Yeah.
No, I believe this is data.
Really?
I take it up with them.
It says more than the top right.
Yeah, it does say model. Which,
No, they're trying to, I think they're, okay, I don't know.
all right,
But the points on M31 and Milky Way are data.
I understand that part.
Yeah. Okay, so what about AGN? Is there any evidence for feedback, in particular in the case of the rapid quenching? So this is the same kind of diagram, and all of what we've plotted here in the green points are the type 2 emission line selected Seyfarths. And this is a key point because, of course, type 2 emission line selected Seyfarths are a biased subset of the AGN population in many ways. And what you find is the classic result that AGN live in the Green Valley, and now this observation that AGN live in the Green Valley tells you the opposite of what we've been told, which is it means these AGN, specifically these AGN, cannot possibly be involved in the quenching of star formation because they come along way too late. So we see Green Valley early type galaxies with nuclear activity. That nuclear activity is hundreds of millions of years after the point at which the star formation actually shut down. Now, this nuclear activity may be involved in cleaning out the system, but it is not the ultimate cause of the quenching. Similarly, you see the late type galaxies, lots and lots of AGN in massive disks. The X-ray astronomers have known this for 20 years, and again, what it means is those guys in the Green Valley where you see some sort of reactivation of the central black hole, they can't possibly be involved in the original quenching of the galaxy because that happened many, many gigayears ago. One possible interpretation is it's just easier to see emission line selected AGN once the star formation rate drops a bit, and it's easier to pick up the emission lines. Another possibility advocated by Rick Davies and co. is that post-starburst or lower star formation rate environments are actually conducive to nuclear accretion in galaxy senses. So anyway, Green Valley, red herring, these AGN have nothing to do with quenching. So for the final part, I'm going to show you some recent observations that we did of the fast quenching track in early times. And so one of the neat things is that I've tied quenching timescales to the fate of the gas reservoir. And I've sort of waved my hand to say, well, the late types, they quench slowly, so all you need to do is turn off the tap, and they'll slowly run out of gas. Whereas the early types, in order to transition rapidly, you need to nuke the gas reservoir to immediately, or effectively immediately, set the star formation rate to 0. So we went and looked with Vestavolk, with crazy exposure times for such nearby galaxies, and we observed 4 Green Valley early type galaxies, so here are their images. They're in the Green Valley, and critically, in this UV optical color diagram, they span the whole range from still very blue all the way to red. And so we traced what happens to the H1 gas along this color sequence, which is a time sequence. So here's the first galaxy. At the center, you see the galaxy itself. In green are radio contours, and in white are the H1 column density. And so what you see is some radio continuum emission from the galaxy, which we believe is completely consistent with sort of the remaining star formation. And you see the H1 gas reservoir. Okay, let's step forward in time. Interesting. The entire H1 gas reservoir is being displaced from the galaxy. Now, if you talk to H1 people, this isn't unusual. H1 reservoirs can look really weird, but I think what matters here is the context, because you have a partially displaced H1 reservoir in a galaxy which just shut down its star formation. So, star formation is fueled by gas. The galaxy just stopped star formation, and the gas reservoir is on the way out of the galaxy. Let's go one step forward in time. Oh, now the gas reservoir is entirely out of the galaxy, but it's still there. So again, this is a very recently quenched galaxy, and here's the gas. Now, this isn't the entire gas reservoir. If you project back, if this galaxy was star forming, how much H1 should it have? It's a higher mass. So we think some good fraction of the original gas reservoir was dissociated, heated, whatever. But the remainder was blown out, was kinetically ejected. And this is why the galaxy has stopped forming stars. And presumably also not restarted. And this is the final one. Again, the entire H1 reservoir has been ejected. And what's really neat is, and this is sort of the intriguing part, well, what process is doing it, these are the radio jet lobes. And they're aligned with the direction in which the H1 reservoir was ejected. Now, the black hole in this galaxy, as far as we can tell, is not doing anything. So what we're seeing here is the after effect. So again, this is a Green Valley galaxy. We can learn something about what happened when it quenched. The gas reservoir was ejected, and AGN at some point was active, but we're really seeing the after effects. So if we want to really get back to the point in time, wind back the clock, the point where this galaxy really quenched, that's hard. And so I got an inspiration last night from the Google Doodle celebrating Germany's win in the World Cup. You see this guy here? That's Paul the Psychic Octopus. Unfortunately, no longer alive, but I think we're going to have to set up a cloning facility at ETH because we're going to need psychic octopodes to figure out which galaxies will quench in the future so we can study them. So thank you very much. I'm going to put up my summary slide. Thank you.
So you were talking all about the early type galaxies in the Green Valley transitioning from the blue cloud to the red sequence.
Yes.
So in my talk on Wednesday, I'll show evidence that quite a few of these could actually be coming down from the red sequence in an excursion because they've created some gas and then will go back up again. How would that change your picture?
So there's two ways to do this. So if you do it the dramatic way, you take your red sequence spheroid and you smash a roughly equal mass star-forming galaxy into it. Okay, I think my picture still applies because you had a major merger and all the gas is brought in anyway by the other partner. Now if you do it another way, you either have a really minor merger or some gas cools or whatever. What would happen is the following. If you just give a quenched galaxy some gas back, okay, that gas will settle into a disk and then it will turn on star formation, it will exponentially decline. So it will reform a disk and it will quench slowly. So it will join the slowly quenching disks. In order to be in that fast track, you can't do what you described, or rather the outcome would look different.
I'll show some plots and then we can do that.
So we had Frank and then Scott.
I had exactly the same question.
Okay, Scott.
I just want to pull off that very slightly. In the studies we've done in Sauron and before, which will relate to Tim's talk on Wednesday as well, it's pretty clear that you can't go from H1 morphology to understand what's happening in the galaxy in these particular objects. You can go from what's happening in the galaxy to the H1 morphology, like you've done. It's very, very hard to go backwards. So your Paul the Psychic Octopus is going to need to look at the H1 after they look at the galaxy properties. So I just want to be a little bit careful about this. Maybe Tim has a lot more galaxies than we've studied. We've studied a couple hundred at this point in H1. We have a really hard time saying that the H1 tells us something about the galaxy. It's not hard to say something about the galaxy and then go to the H1 and say, okay, what's going on in the H1? So.
My suspicion, this is largely due to the fact that Sauron is a survey of early type galaxy with a strong bias to the ones that are already red. I think you have like a few that are sort of greenish.
We've also done, 20 or so that are not, outside of the Atlas Sauron thing. We've done a few that, we've done 20 or so that are completely different, that do include galaxies like what you and Scott were talking about. But even in those galaxies, we don't see a lot of connection between the H1 and the H1 properties and the galaxy itself. Right? So it doesn't, what I'm trying to say is, be careful about going from H1 to galaxy to optical star formation history properties. But you can actually go the other way, because it turns out that if you know about the star formation history, you can generally go to H1 and say, if there's H1, what does it look like? And that actually turns out to work. It doesn't work the other way because there's too much scatter in the H1 properties. So, maybe we can talk about this offline.
Okay, yeah, let's talk about this offline.
Okay, Marianne?
Yeah, maybe you have in the paper, but I suppose that you have to follow also how the luminosity change, right? With your different, if you have this information that went earlier or not. So if you have more information going on, the luminosity is increasing. And so when you show your tracks there in the color, what happens if you have something against the luminosity?
Well, the color tracks don't include any luminosity.
Right. So I suppose that you should follow also what happens with really the total luminosity. Does it match the observation that the data you have?
What data are you thinking of matching? Mass functions or luminosity functions?
Luminosity. Okay. So you have when you have a slow star formation that goes for a while. So if the luminosity becomes too large because you keep forming star, do you see?
Right. So, well, I don't think that would happen. So let's imagine a disk galaxy that has a fixed gas reservoir corresponding to what it should have to remain on the main sequence, and then we don't allow it to get any further amount of gas. So you have a gas fraction, we measure gas fractions in galaxies, and so you could say the maximum in stellar mass this galaxy could grow is if you turn all that gas into stars, which probably isn't going to happen, but that means that in terms of mass, these galaxies aren't going to grow much further, certainly not in the uncertainties of stellar masses.
Okay,
Yeah, sorry,
so two more questions.
I had a quick question about the final data you're showing with H1. Do you know anything about the environment of these galaxies?
They span a range of environments, though they're not particularly near cluster centers or group centers where you would expect strong environmental interaction.
So actually, I had a similar question. So can you exclude ramp pressure effects? And that's the first one. And the second one, what would the physical mechanism of the AGN actually driving this gas on?
So first, can you exclude ramp pressure stripping? We're fairly confident that we can do that just because of the position of those four objects relative to their local environments. For the second question, what would the mechanism be? I don't know. I'm not even sure that it has to be the AGN. I think the alignment between that radio jet and the direction in which the gas is expelled is intriguing, but that's one object, right? And the universe is full of peculiar objects. So I wouldn't even want to be nailed down on it has to be the AGN.
Okay, so we're going to reconvene at 2 after lunch, and Greg's going to make an announcement.
Well, just that lunch is downstairs.